So last time in class we talked a little bit about states of matter, phases of matter you could call these. You'll recall the ones that we need to be concerned about are solids, liquids, and gases. In today's video we're going to talk about how we transition from one phase to another, and then we'll follow this up next time in class with some demonstrations and some experiments later. So first of all, we've got to talk about how particles are moving around in a substance. I know that we haven't talked yet much about atoms or anything, but I'm sure you remember that everything is made up of tiny small molecules or atoms or particles. Let's just call them particles. Little tiny parts of things is basically what particle means. We've got the diminutive added on to part. So everything's made up of these little particles. And the particles are always in motion. This forms the basis of something called the kinetic molecular theory. Let's talk about it for gases, first of all, ideal gases, because it's a little bit easier to understand if we approach it from a standpoint of gases. So, in an ideal gas, we'll talk about what the ideal means later this year, you've got large numbers of tiny particles that are celebrated by fairly big distances for their size. When these particles interact with anything, they have elastic collisions. Elastic just means like a rubber band. You stretch it, you let it go, it snaps back. That's an elastic collision. Things collide and go back to the way they were before. They may change direction, but they don't lose energy. These particles are in continuous rapid motion. There's no forces of attraction between the particles, so it's not like the solar system where you have planets in orbit around the sun. These things are just going to bounce off and go on their way, more like pool balls, billiard balls. And the important thing for us today, the temperature of the gas depends on the average kinetic energy of the particles. Here it is in mathematics language. Ke, that's kinetic energy, equals 1/2 times the mass of the particle times its velocity or speed squared. This is going to be very important because notice from this, temperature is related to the motion of the particles. Temperature in a solid, liquid, or gas, I know we've mostly been talking about gases, but this Ke equals 1/2 mv squared holds true for any of them, is related to the motion of the particles. So, what is it then that's going to make a liquid different from a gas? And that's right, in a liquid, the particles are going to have less kinetic energy than in the gas, so they're going to be moving slower. In a liquid, there's more attraction between these particles. They're not able to fully get past each other. In a solid, there's even more attraction. These particles are stuck together in a certain shape. They can still wiggle, they can still vibrate. That is going to increase kinetic energy and have a temperature at all. But they're not going to have the same freedom of movement. So it all has to do with molecules moving is what temperature is doing. Particles, right, are moving slower in liquids and even slower in solids. So phase changes. Real quick, let's just go through the names. When we change phase, we move from one state, one phase of matter, to another. Solid to liquid, melting. You probably know that. Solid to gas is something called sublimation. Dry ice does this. At regular atmospheric pressure, carbon dioxide in dry ice moves directly from a solid into a gas. That's why it's called dry ice. It doesn't leave any liquid behind. Liquid to solid is freezing, you know that. Liquid to gas, vaporization. You may have called it boiling before, but boiling is technically something a little bit different, as we shall see. Gas to liquid, that's called condensation. Condensation, like when you have a cold water bottle, water gathers on the outside of it from the air and drips down onto the table. gas to a solid, the opposite of sublimation is going to be deposition. So, phase changes. If the difference in phases has to do with the kinetic energy involved in the particles, then it follows that phase changes would have to do with energy. So what causes a phase change? It's going to be an increase or decrease in the energy that's in that material. A very easy way to study this is with a graph over to the right. Let's just think about water. Now water, just like any substance, can be a solid, a liquid, or a gas. Ice is still water, steam is still water. So, if we have a sample of ice, we can increase its energy. We can put energy into it, most likely with some sort of hot plate or flame. As this happens, the ice is going to get warmer and warmer. You can note here on the graph, temperature is here on the y-axis. Energy is essentially going to be here on the x-axis. It says time here, but imagine that's the amount of energy going up. And what you will note is that the temperature of the ice goes up until it levels out right here. What is happening right here is a phase change. The water is transitioning from a solid to a liquid, so it is melting, and the temperature doesn't change. During a phase change, the temperature will not change because all the energy, as we keep increasing the energy, that energy is going into melting. That energy is going into rearranging the particles, not actually increasing their speed, so the temperature is not going up. Once all of the ice has been melted, once the water is all liquid, notice temperature going up and up and up and up some more until, look, levels off again. This is another phase change, going from a liquid to a gas, so that's vaporization. Temperature will not go up until it's all a gas, and then the temperature will go up and up and up and up, essentially forever, if we keep putting energy into it, because those particles can move faster and faster and faster. There's no really more phase change that water will undergo, at least nothing that we'll do in the lab. We'll go over this again in class tomorrow. It's a very important graph to understand. Vapor pressure. Now bear with me a little bit on this. This will probably be the most complicated thing from this video. But even if you have a substance that is a liquid, that's in the liquid phase, some particles are still entering the gas phase from its surface. These particles are producing a pressure, a vapor pressure, if you will. What is pressure? Well, you've talked about pressure before in other classes. There's air pressure in tires, or if you push down on something, that's a lot of pressure. Or if you feel the weight of school pushing down on you, you say you're in pressure. Pressure, in a science standpoint, is a certain force over a certain area. So, these particles are coming off. The more particles that come off, the more pressure they create, because that's a greater force. If you have a liquid that's called volatile, such as alcohol or gasoline, they have a very high vapor pressure, meaning they are evaporating quickly. They're fast quickly anyway, changing from a liquid into a vapor. Boiling. Boiling is going to happen when the vapor pressure of the liquid, so the pressure of those particles coming off the surface, reaches the pressure of the atmosphere pushing down on the surface. When those two are equal, that's boiling. When boiling happens, you see all the little bubbles forming. You've got vaporization going from liquid to a gas, not only here at the surface, but every place inside the liquid. That's a very special type of phase change there when boiling occurs. You can make things boil at room temperature. You can make water boil at room temperature if you remove the air pressure on top of it, which you can do with a vacuum chamber. The water's not hot at all, but it will still boil. Remind me next time in class and I'll show you a video of that. One last thing to talk about today, and that's a phase diagram. Take just a few minutes and go ahead, or a few moments anyway, and go ahead and look at this diagram. Now you should see right away that along the x-axis we have temperature, along the y-axis we have pressure. What a phase diagram is showing you is when phase changes will occur based on temperature and pressure. Right here, 1 atmosphere of pressure, that's about the air pressure at sea level. That's normal air pressure for us, essentially, unless you're up in the mountains. So let's just follow that line here. You can see that as you go along this line, you've got solid water, liquid water, and vapor, gaseous water, steam, just as we would expect. But you can also note that some interesting things will happen here. At a point where water normally freezes, if you make the pressure go higher and higher and higher, you can make that water change into a liquid, even though its temperature is colder. That's actually what is happening for ice skaters. When ice skaters are on ice, they're actually skating on a thin layer of water. Their skates put so much pressure on the ice, it causes it to melt again. If we go down, if we make the pressure less and less and less, there's a very special point for water right here called a triple point. Look at the graph. See if you can figure out what triple point means. And indeed, it is called a triple point because solid, liquid, and gas, all three are existing at the same temperature at the same time. It's pretty crazy. Critical point is the temperature is now so high, it's not going to be able to exist as a liquid anymore at any pressure. So this is a phase diagram. We'll take a look at some of these for different substances in class. They're fairly easy to understand as long as you just remember temperature here, pressure here. For normal experiments that we'll do in chemistry, all you have to do is follow the pressure line for 1 atmosphere of pressure. That's normal air pressure. Okay, great. Don't forget to do the whisk, and don't forget to bring in something for class if you want to freeze it tomorrow. Thanks for listening.